Hey, what's up, guys? This is Cheng here again. So today, let's take a look at this 947 most stones removed with same row or column. Yeah, I think this is a great problem. I don't know why so many people downvote this problem. Okay, so on the 2D plane, we place stones at some integer coordinates points, and each coordinates point may have at most one stone. Basically, there's no overlapping stones on a single location coordinates. So now a move consists of removing a stone that shares a column or a row with another stone on the grid. Okay? And what is the largest possible number of moves we can make? So this is the part we need to be to be careful here, right? So move consists of removing a stone that shares a column or a row with another stone on the grid. So what does it mean? It means that you can only remove a stone if there's another stone that has shares at the same row or column. So a few examples, right? So let's say we have a like this grid here. Okay. Okay. It doesn't really matter. So let's say we have a bunch of stones here. We have one stone here and we have one stone, two, three, four, five. Yeah, something like this, right? Or we have another one here. So let's say we have one, two, three, four, five, six. Or another one is right here. And so how many, it asks you to find what's the largest possible number of moves we can make, right? So how many, what's the maximum stone we can remove? For example, this one, obviously there's no way we can remove it because it doesn't share any, there's no other stone who is sharing the same row and column with this one. So that's it's basically itself. And as you guys can see here, so we have three stones here and two stones here and one stones here. Basically we can this like six stones are like within the group, right? So what can we remove? So the best strategy is always remove from the side, right? So basically we remove this one first, and then this one, and then probably this one. Yeah, and then we can remove. So the next one, we should remove either this one or this one. We cannot remove this one because if we remove this one, so neither of these two can be removed again. So we have to remove this one first and this one first, and this one next, right? In the end, we only have one stone left. So what does this strategy telling us? So it's telling us as long as those stones, right, are connected either by the row or column, then we can remove all the other stones except for the last one, right? So what does it means that, as if we are connecting this one with this one and with this one. So it's as if we have island here. So now the problem converts to what? To find how many islands or how many groups on this 2D plane, which is connected by the same row or column. And if we find that number of columns or the number of groups, all we need to do is that we just need to use the length. Let's say the length of the stones is n here. We just need to use the n minus what? The groups, right? So the problem is now is the how can we find how many islands or groups on this 2D plane? I mean, I think you guys all have seen this problem. How many the islands on the 2D grid, right? So this is similar, but the only difference is the on that islands problem, we only have four options, which is the up, down, left, and right. But for this, it's different, right? Basically, it could be as long as they have the same row and columns, right? We can keep expanding this group like this, and this. So for that, I'm going to use like we can use either DFS or BFS to traverse all the possible, nodes in the same group. So that's the first approach. So the second one is what? As you guys can see, we are actually we're talking about connectivity issues here, right? So every time when we trying to solve these connectivity issues, we should always try to use the union find. And that's why today I'll be doing two solutions. The first one is the regular DFS search, and the second one is the union find. Okay. All right. So first thing first, the DFS, which is the regular approach. So to do the DFS search, right, we have to somehow build the groups first, so that at each of the coordinates, we know what are the candidates, right? Basically, we need to know. Let's say that we have I and J, right? That's the current coordinates. We need to know what are the other points, or what are the other stones that share the same the row and column. To do that, we just need to do a pre-process. Okay, I'm going to have like how should I call this one? Um, I'll just call it a graph maybe, or yeah, I'll just call it a graph here. Maybe this is not a very good name, but I'll just stick with that. Basically, this graph uh, stores like all the key for this graph. The key is either the row or the column, and the value is the pair, is the coordinates that share on the same row or column. Okay, so to do that, you have I and J in the stones, right? And then we have a graph I dot append I and J. Okay, so here, um, so this is something you guys need to be noticed here. Since we have we have row and column, and the row and column, they could um, they could be on the same, they could be on the have the same numbers, right? So what I mean the same number, I mean this, if we have like 1 0 and 0 1. So here we have I equals to 1 and j equals to 0, right? Here we have I equals to 0 and j equals to 1. We cannot simply use the j here, because that in that case we'll mix the I and j with one number, right? So a different way of solving this problem, we have some options here. The first one is if we can add like numbers on top of it, right? We add like if we know the range of the stones here, we can add like a big enough numbers so that we can distinguish that. But here, we have like a stones numbers length plus one. Ideally we can just simply do a j plus 1000, right? So that we know this I and j will never be the same, right? So that's one thing. The second thing is we can use a trick here. We can use a bitwise not to convert all the j value to its not value, bitwise not value. So why we cannot use negative, right? So the issue is like it's for zero, right? So if I and j are the same for zeros, as you guys can see, negative zero is also zero. So that's why we need to do a bitwise not. So for bitwise not, we have like, so what is this one? It's equal to -1, right? So bitwise 1 equals to -2, right? That's why, that's how we use this trick to distinguish the row and the column. So this is a little bit trick you guys need to be remember. It's better to know. Okay, so now we have like I and j. So after this one, we have a graph. The key is like the row and column, and the we have a list of the coordinates on that. So now the next step is simply the regular DFS search, right? So I'm going to have a groups here equals to 0. Okay. So for I, j in stones, okay. If ij is not in the visited, okay, right? So we do the groups plus one, right? We increase the groups plus one, and then I'm going to have like a stack here. So the stack, I'll be using the stack to traverse the current group, right? And then we have visited dot add ij. So now we have a while stack here. So basically, with this graph here, we can use this while loop here to traverse to find all the coordinates that's sharing the same, basically are in the same group. Okay, and now we have a current I and the current j equals the stack dot pop, right? So here it doesn't really matter. You can either use like a queue to do a pop left, or you can do a just like what I did here, what I'm doing here. I just simply use the stack doing the pop, because the sequence doesn't really matter, because anyway will be traverse all of the nodes, right, in the same group. So either DFS or BFS works. So now for new I, new j in what? In the graph of I. So first we traverse all the coordinates that's on the same on the same row here, right? So if the new I and new j are not visited, okay, so right, then we do a stack dot append, right? Append this thing, and we also need to add it to the, okay, right? Yeah, so that's for the row, and do the same thing for the column. I'll just copy and paste here. So here we do a bitwise not j, right? Sorry, here. So it should be current I and current j, right? So basically after this while loop, right? I mean everything that's inside in the same group will be added to the visited set here, and we also increase the groups here. Okay, and after this for loop here, we have the groups we need, and we just simply need to return this the length of stones, right? Minus the groups, right? So why is that? Because we already find our strategy, which is which for each group there will be only one stone left in the end. So that's why the total number, the max number of stones we can remove is the total number of stones minus the number of groups, right? So run the code, accept it, submit. All right, cool. And yeah, how about space and time complexity, right? So, I mean, space complexity is pretty straightforward. We have a space complexity is O of n, right? Because we have like this graph stores all the coordinates for the stones here. How about time complexity? So the time complexity, we have a n on the outer loop here, and then for each of the stone here, we will be and yeah, we'll be looping through all the elements on the same row here. Right, so I think worst case scenario, we need to do a ON of search, ON of loop here. So yeah, I think space time complexity should be a n square for this DFS solution here. Yep. So that's that. Next, the union find, right? So it's always a good thing, good practice to try the union find. I mean, actually, union find is exactly designed for this kind of problem to find the groups, right? As you guys can see, all we need is we just need to find how many groups, right? This like each nodes, each stones can form, and they should be joined a union uh, by their row and column. If you guys know the union find, right? So first we need a find, right? We need a find and we need a union. Okay, so I'll just define those two functions here, right? Union and find, x and y. So to start with, right? I mean, for the regular union find solutions, we will need to define their parents first. So what does their parents mean, right? The parents means each node will has its own as its parents. But we have like, as you guys can see, we have the stones range from 0 to 10 to 100,000. So if we want to initialize parents at the beginning, basically we will initialize the length of 10,000, right? 100,000 stones. That will be too much. So what can we do? So instead of using a list here, we can simply use a dictionary here, right? And we only initialize this parents whenever we see a stone. Okay, basically when we only do the initialize its parent when we do the union the first time. Okay, so now let's implement the find here. So the find, that's a template, right? If the x is not same as the parents x, right? We do what? We do a path compression, right? Plus the recursion call, right? So find parents. That's how we do the path compression, right? And then we return the parents x. Okay, yeah, so that's the find and the union here, right? So like I said, since we didn't initialize the parents at the beginning, it means that so whenever we do the union here, and we should initialize this parents to this x with its own value at the first time. So how do we do it? We do a parents um, parents dot set default. There's like functions in Python. So we set this key with this value. If it's not been set before, that's the built-in function. Or we can simply do a check. If x is not in parent, we set this to x. Otherwise, we skip that. Basically, that's what the set default is doing it for us. All right, same thing for the y here. Set default and y and y. Right, so here now we have a parent here. And the rest is just the regular union find template. We find R1, root 1 with X, and we find root 2 with Y. If R1 is not the same as R2, we do what? We assign one parent to the other. So here we either do R2 or R1. I mean, so here, as you guys can see, I'm not doing any rankings here. So, I mean, ideally, I should have a rank system. That's gonna be another performance, but for this problem, this is enough. And yeah, so now, right? So ij in the stones, we have the union find structure here. So all it's left just to try to union those each I and the columns here. All right, so we just do a union I and j. Oh, yeah, so same thing here, right? When we do the J here, we will do a bitwise NOT here to distinguish the row and the column. Okay, so that's it, right? That's as simple as it is. So after this union here, so what do we have in this parent here? So we have a parent. So the parent will store the key is each of the stones here. Sorry, the key is for each of the every row and column for all the stones. And what we need the number of the roots because the number of roots represents how many groups we have created here. So that's why I'm gonna have a roots equals to what? Equals to the yeah, I can simply use a set here because multiple key will have the same root after union, right? I can simply use a root here, and this will give me the unique roots. And in the end, I can simply do a length of this one to give me how many distinguished roots, right? So mm, we have a key, right? So for the key in the parents, right? And I have a root here. So root is the find of the key. Okay. Yeah, so the key is either the row or column. Now we find the roots, right? And I just do a roots dot add root. Okay. Now same thing, return the length of the stones minus the length of the roots. Yeah, that's the number of the groups we have here. Yep. Run the code, accept it, submit. Cool. Yep. So also accept it. And as you guys can see, the union find code, it's much simpler, right? And the time complexity, right? So we have O(n) here, right? O of n, and then we have, for a union find, if we do a like a ranking, if we do a rank here, optimizations here, so the find and the union they should be treated as like close to O1. So this should be also is O1, and should be also close to O1. Yeah. So for the union find, if we do everything correct and the space time complexity should be close to O of n, which is much faster than DFS or BFS search. Okay, and the space complexity is also O of n, right? Same thing as this one, time and space. Yeah, cool. I think yeah that's it. It's a very I think it's a very good practice for either the DFS search, DFS, BFS, and then the groups, and how can you union uh, create a groups where for the row and the column. This is very helpful. I think later on there will be another many problems. Will maybe we can utilize this kind of technique, especially for how can we handle the row and the columns. And the most important thing is that how can we utilize the unified concept to help us create a groups, right? That's why the unified is also called a disjoint set, right? Because at the beginning everything was separated, and then we do the unions based on some conditions. In this case, is the row and the column. And after that, we have the groups we need. And in the end, we simply use the number of groups, and that can give us the result. So, guys, remember, try to use the union find as many as you can. It's a very powerful technique. Okay, cool, guys. Thank you so much for watching these videos. Stay tuned. I'll see you guys soon. Bye bye.